I welcome you all in the fourth lecture on psychrometry. In this session on psychrometry, we shall solve some numerical problems related to various psychrometric properties. This session will help you understand if some of the psychrometric properties are given to us, then using the psychrometric relationship, how the other psychrometric properties are calculated. Now we begin with the first problem on psychrometry, and the statement of the problem goes this way. A mixture of dry air and water vapor is at a temperature of 21 degrees Celsius under a total pressure of 736 mm of Hg. The dew point temperature is 15 degrees Celsius and we have to determine the partial pressure of water vapor, relative humidity, specific enthalpy of water vapor by all three methods, enthalpy of air per kg of dry air, and lastly the specific volume of air per kg of dry air. Having read the statement of the numerical problem, we identify the following things: that the dry bulb temperature has been given as 21 degrees Celsius. The dew point temperature has been mentioned as 15 degrees Celsius and the total barometric pressure is given as 736 mm of Hg. So first of all, what we shall be doing is we shall determine the saturation pressure corresponding to the dew point temperature of 15 degree Celsius. Because when we locate this dew point temperature on the temperature versus entropy plot, let us consider that the partial pressure of the water vapor is PV. So here we have got this PV, and point number A is nothing but the thermodynamic state of the water vapor, which is present in the given sample of the moist air, which is appearing at a temperature of 21 degree Celsius. So here this small t is nothing but the dry bulb temperature of the given sample of the moist air. So this line is for 21 degree Celsius constant temperature line. Point number A is the thermodynamic state of the water vapor in the given mixture of dry air and water vapor, and point number G is corresponding to its dew point temperature. So when we have been given this dew point temperature, so we will go in the reverse manner. So looking at 15 degrees Celsius in the steam table, we shall first enter into the temperature column and look for the 15 degrees Celsius, that is the saturation temperature value, and the corresponding value of the saturation pressure is 0.01704. So there may be a slight difference between the values taken from the different tables. So here at 15 degrees Celsius the saturation pressure is 0.01704. so this is nothing but the partial pressure of the water vapor. So here the value is 1707.5 Newton per meter square, or 1707.5 Pascal. Now we know that at 21 degrees Celsius itself, the pressure at point number C is nothing but the saturation pressure at given dry bulb temperature. So again we shall move to that same steam table and look for the pressure value corresponding to 21 degrees Celsius dry bulb temperature. So here we enter into that steam table and look at the temperature value. Saturation temperature is given as 21 degrees Celsius. So this is corresponding to the point number C. So corresponding to this 21 degrees Celsius, the saturation pressure is given as 0.02485 bar. So this is going to be 2489.81 Pascal. So having determined these two pressures, so one is the partial pressure corresponding to point number A, that is the partial pressure of water vapor, and the pressure corresponding to point number C, this is nothing but the saturation pressure PVS. So the temperature at point number A and temperature at point number C are same. So now we determine the relative humidity. Relative humidity, as we defined earlier, is nothing but the ratio of two partial pressures, that is the partial pressure of the water vapor at a given temperature divided by the partial pressure of the water vapor when the air sample has been brought down to the saturation at the same temperature. So PV upon PS multiplied by 100 will be the relative humidity value. So dividing this 1707.5 by 2489.81, multiplying it by 100%, so the relative humidity is obtained in percentage as 68.58%. Now we go for determining the specific humidity denoted by symbol omega or small w. The expression, I hope that you guys still be remembering that expression for the specific humidity. It is 0.622 PV divided by PA, or it is going to be 0.622 PV divided by P minus PV. Here PV is nothing but the partial pressure of water vapor, and PA stands for partial pressure of dry air part. So the PV plus PA is going to be equal to the total barometric pressure or the total pressure of the given sample of moist air. So from here we determine the value of PA. It is nothing but P minus PV. PV we have already determined earlier with the help of dew point temperature. So we just substitute all these values in this expression for the specific humidity 0.622 PV divided by P minus PV, and solve this, and finally what we get is 0.011 kg of water vapor per kg of dry air. Now we move on to, now we shall determine the enthalpy of specific enthalpy of water vapor contained by three methods. While discussing the enthalpy of moist air, we came across an expression that is specific enthalpy H is equal to HA plus omega times HV, where HA is nothing but the enthalpy of dry air part, omega is the specific humidity, and HV is the enthalpy of specific enthalpy of water vapor content or the moisture content. So the thermodynamic state of the water vapor which is present in that moist air sample is basically at point number A. So ultimately what we need is we need to determine the specific enthalpy of water vapor corresponding to its thermodynamic state at point number A with respect to some reference or the datum. So the datum value or the reference value, we have taken it as 0 degrees Celsius. So at 0 degrees Celsius we assume that enthalpy of the saturated fluid, that is liquid water, is 0 at 0 degrees Celsius. So with respect to this datum reference, we need to determine the change in enthalpy up to point number A. So there are three ways of calculating the specific enthalpy at point number A. Either we calculate the enthalpy at point number C at A or B. It is not going to create any difference because all these 3 points, point number A, C and B, they lie on the same temperature line, that is corresponding to the dry bulb temperature. Since the partial pressure of the water vapor is very low, and at such low value of the partial pressure, whether the water vapor exists in superheated vapor form either at point number A or B, or it appears in the saturated vapor form, it more or less behaves like a perfect gas, and for a perfect gas its enthalpy is solely a function of temperature. So since the temperature at A, B, C, it is same, so enthalpy at point number C, A and B, it is also going to be same. So there are three ways of calculating the specific enthalpy of water vapor. One is moving from that reference value of 0 degrees Celsius and moving along the saturated liquid line up to the dry bulb temperature. So there will be a sensible heat added to the liquid water. So that is going to be simply Cp of water multiplied by delta T. So delta T here is T, temperature of the water, minus 0 degrees Celsius. So this is going to be Cp of water into T plus the latent heat of vaporization at dry bulb temperature of 21 degrees Celsius will bring us at a point number C. So that is exactly what we need, is the specific enthalpy at point number C. This is the first method of calculating the specific enthalpy of water vapor content. So for that purpose, what we are going to do is we are going to calculate the specific enthalpy at point number C. It is going to be Cp of water into T. So this is moving from this datum reference value up to here, plus enthalpy of vaporization at 21 degrees Celsius. So this value we shall take from the steam table. Enthalpy of vaporization at 21 degrees Celsius, we will take it from the steam table. So this value is 2452 kilojoules per kg Kelvin. So we substitute all the values. Cp of water is 4.1686, temperature in degrees Celsius is 21, plus specific that is enthalpy of vaporization at 21 degrees Celsius. So that gives us a value of 2540 kilojoules per kg of water vapor. Then we calculate the specific enthalpy at point number A using this second method, that is moving from this reference state up to the dew point temperature. So dew point temperature was given as 15 degrees Celsius here. Then moving along this path F to G. So again the temperature at point number F and point number G, it is same, 15 degrees Celsius, and then moving along this constant pressure line till we acquire the point number A. So temperature at point number A is obviously equal to the drivable temperature of 21 degrees Celsius. So three distinct that is heating regimes are there. First is sensible heating of water from 0 degrees Celsius to its dew point temperature of 15 degrees Celsius. Then latent heat, that is the phase change process, will be there. So adding latent heat of evaporation to the water, its phase changes from F to G. Then superheating of these dry saturated vapor from point number G to point number A. So here we go with that expression. So HA is going to be Cp of water into Td. Td is nothing but, that is the dew point temperature minus 0 degrees Celsius. So Td minus 0 is nothing but Td. So Cp of water into Td plus latent heat of evaporation at 15 degrees Celsius plus Cp of vapor. You need to remember this value. Cp of the vapor is going to be 1.88. We discussed about it in the previous lectures, multiplied by the temperature difference of point number A and point number G. So this is 21 minus 15. So 4.1686 Cp of water. Temperature is now 15 degrees Celsius. This is the enthalpy of evaporation at 15 degrees Celsius. This value we shall again obtain with the help of steam table. So going to that, the saturation temperature of 15 degrees Celsius, and look for the value of the specific, that is latent heat of evaporation. 1.88 is nothing but CPV, and T minus TD is 21 minus 15. So we again determine this value. It comes out to be 2540.3 kilojoules per kg of water vapor. Then third way of calculating the specific enthalpy of the water vapor is moving along this 0 degree Celsius line from this liquid state to the vapor state, dry saturated vapor state. Only the latent heat of evaporation at 0 degree Celsius would be added, and then moving along this constant pressure line from this point number G, which appears at 0 degree Celsius, up to the point number B here. So enthalpy, specific enthalpy at point number B is going to be calculated as that is equal to, that is latent heat of evaporation at 0 degree Celsius plus Cp of V into temperature at point number B minus temperature at point number G at 0 degree Celsius. So this is going to be 21 minus 0, that is 21. So it is going to be 2501, and that is a very easy figure for us to remember, that latent heat of evaporation of the water at 0 degree Celsius is 2501 kilojoules per kg Kelvin plus 1.88 multiplied by 21. So it also gives us the same value, 2540.5 kilojoules per kg of water. Now we move on further to calculate the specific enthalpy of moist air. I hope that all of you are still remembering the expression for the specific enthalpy of the moist air that we derived earlier. The specific enthalpy of the moist air is given by expression H equal to Cpa into T plus omega times Hv, where Cpa is the specific heat at constant pressure for the dry air part, and its value is 1.005 kilojoules per kg Kelvin. T is the temperature in degrees Celsius, and it is nothing but the dry bulb temperature. Omega is the specific humidity. Hv is the specific enthalpy of the water vapor content that we have calculated using three different ways in the previous slide. So we just put all these values in this expression for specific enthalpy of the moist air, 1.005 into temperature, dry bulb temperature in degrees Celsius, plus specific humidity. We calculated it earlier, and Hv is 2540.3 kilojoules per kg of water vapor. So it is going to be 49.0 kilojoules per kg of dry air. Now the specific volume of air is equal to the volume of 1 kg of dry air or 0.011 kg of water vapor. So we will be calculating the specific volume based on the dry air part as well as based on the water vapor content. Now, since we have been given a total barometric pressure of 736 mm of Hg, and we know that 760 mm of Hg is corresponding to 1 bar or 100 kilopascal. So this total barometric pressure of 736 mm of Hg would be corresponding to a figure of 98125.2 Pascal. Now the partial pressure of the water vapor we have earlier calculated as 1707.5 Pascal. So with the help of that expression we determine the partial pressure of the dry air part as the total barometric pressure minus the partial pressure of water vapor. So this figure comes out to be 96417.7 Pascal, that is the partial pressure of dry air part. So with the help of this expression, we calculate this VA equal to RA into T divided by PA. RA is nothing but the gas constant for the dry air part. It is 287.3. Temperature, mind it, here the temperature has to be in Kelvin. Dry bulb temperature is 21 degrees Celsius plus 273, that makes it in Kelvin, divided by the pressure, that is the partial pressure of the dry air part. It has to be in Newton per meter square or in Pascal. So this value is 96417.7 Pascal. So that gives us a figure of 0.876 meter cube per kg of dry air. Now the similar calculation for the specific volume of the air may be based on the water vapor part also. So let us try that also. So VB is going to be RV into T divided by PV. Now the RV is nothing but the gas constant for the water vapor content, and it is 461.5. Temperature is again in Kelvin. That is the dry bulb temperature plus 273 divided by partial pressure of the water vapor in Newton per meter square or in Pascal. So just putting in all the values will give us a figure of 0.874 meter cube per kg of dry air. So there is not much significant difference between the specific volumes calculated here. If we consider it only up to the second place of the decimal, and these are going to be one and the same thing, 0.087 meter cube per kg of dry air. Now we go with the second problem on the psychrometry. Statement of the problem is like this. The humidity ratio of the atmospheric air at 28 degrees Celsius dry bulb temperature and 760 mm of Hg is 0.016 kg per kg of dry air, and we have to determine the partial pressure of water vapor, its relative humidity, the dew point temperature, and the enthalpy of air per kg of. So let us just quickly look at the values which have been given to us. The dry bulb temperature has been given to us as 28 degrees Celsius. A specific humidity is given to us as 0.016 kg per kg of dry air, and the total pressure is given as 760 mm of Hg. So it is definitely equal to 100 kilopascal. Now we go with the expression for the specific humidity or the humidity ratio. So this small w is 0.622 into PV upon P minus PV, where PV is the partial pressure of water vapor and P is the total barometric pressure. So omega is given as 0.016, then putting in the values 0.622 PV divided by P minus PV. Here the P is given as 760 mm of Hg, so it is equal to 101325 Pascal or Newton per meter square. So with the help of this expression we solve it for PV and determine the value of PV as 2540.6 Newton per meter square, or it is equal to 19.06 mm of Hg. Now, with the help of the steam table, we determine the saturation pressure at 28 degrees Celsius dry bulb temperature, because the PS, that is the saturation pressure, is always corresponding to the dry bulb temperature. So we just move to the 28 degree Celsius here in the temperature column of the steam table and look for the next column value, that is always for the pressure, saturation pressure. So it is 0.03778. So it is going to be 3778 Pascal. So with the help of that we determine the relative humidity, which is nothing but the PV divided by PS. So it comes out to be 67.2%. Now we know that the dew point temperature is what? It is always the saturation temperature corresponding to the partial pressure of the water vapor. So partial pressure of the water vapor is given to us as 2540.6 Newton per meter square. So we look for this value of saturation pressure in the steam table. So 2540.6, this lies somewhere around 21 degree Celsius. So with the help of that interpolating the values between that 21 and 22, we calculate the dew point temperature as 21.1 degree Celsius. Now, in order to calculate the specific enthalpy of the moist air, we shall first determine the specific enthalpy of the water vapor part. So we know that we have earlier calculated the dew point temperature as 21.1 degrees Celsius. So ultimately the point number A here, it lies on the dry bulb temperature line, and the temperature at point number G, it is 21.1 degrees Celsius. So corresponding to this saturation temperature of 21.1 degrees Celsius, there is a constant pressure line which is nothing but the partial pressure of the water vapor. So ultimately we need to determine the change in enthalpy from the reference state of 0 degrees Celsius right up to point number A. So moving along this constant pressure line on the temperature versus entropy plot, so from 0 degrees Celsius to F is nothing but Td minus 0 multiplied by Cpw. So Cpw, that is the specific heat at constant pressure for the water, is 4.16 multiplied by this Td minus 0 is nothing but Td. It has to be in degrees Celsius, total 21.1 degrees Celsius, plus the latent heat of evaporation at 21.1 degrees Celsius can precisely be interpolated using the steam table. So we definitely at this point of time require the steam table in order to calculate the enthalpy of vaporization at 21.1 degrees Celsius. So using the steam table, this value is coming out to be 2451.76 kilojoules per kg Kelvin. Now this CPV, here we are moving from this point number G up to the point number A. So this is nothing but the superheating at constant pressure line. So CPV into temperature at point number A is equal to dry bulb temperature, and temperature at point number G is equal to the dew point temperature. So this T minus TD multiplied by CPV. So just putting in all the values and calculating it gives us a figure for that HV as 2553.07 kilojoules per kg of water vapor. Now the enthalpy of the dry air part, we know it with the help of expression Cpa into T, it can easily be calculated. It simply depends on the dry bulb temperature. So Cpa is 1.005 into temperature, it has to be in degrees Celsius in this expression. So the dBT has been mentioned as 28 degrees Celsius. So enthalpy of the dry air part is 28.14 kilojoules per kg of dry air. Now inserting these two values of, that is specific enthalpy of dry air part and the specific enthalpy of the water vapor content in the expression for the specific enthalpy of the moist air, H equal to HA plus omega times HP. So that figure comes out to be 68.99 kilojoules per kg of dry. Now we look at the third numerical problem on psychrometry. We have been asked to calculate relative humidity ratio, dew point temperature, density and enthalpy of atmospheric air when its dry bulb temperature is 35 degrees Celsius, its WBT, that is wet bulb temperature, is 23 degrees Celsius, and the barometer reads 750. This particular problem, we have been given the dry bulb temperature, we have been given the wet bulb temperature and the total barometric pressure. So you would notice that in this particular problem we have not been given the value of dew point temperature. So we are now helpless in order to determine the partial pressure of the water vapor, because the partial pressure of the water vapor is always corresponding to its dew point temperature. So when we have been given the value of wet bulb temperature, we came across one empirical correlation given by the carrier. So using this empirical correlation given by the courier, we can obtain the value of the partial pressure of water vapor PV in terms of the wet bulb temperature denoted as T dash. So you need to remember this expression PV equal to PV dash, where PV dash is nothing but the partial pressure of the water vapor corresponding to its wet bulb temperature. P is the total barometric pressure, PV dash is same thing, that is the partial pressure corresponding to WBT. T is the dry bulb temperature, T dash is the wet bulb temperature, and again in the denominator part this T is the dry bulb temperature. So all the values have been given to us. What we do first is we determine the saturation pressure corresponding to 23 degrees Celsius of wet bulb temperature using the steam table. So this value comes out to be 21.06 mm of Hg. Now this is basically a difference of the two pressures. So it all the unit for both the things, that is P and PV dash, they have to be consistent. So they have to be same. So total barometric pressure is given to us as 750 mm of Hg, and PV dash we have determined again this partial pressure of water vapor corresponding to WBT in terms of mm of Hg. So we will put this value here only. Then T is 35 degrees Celsius is the dry bulb temperature, T dash is WBT 23, and rest of the values are already there. So PV, that is the partial pressure of the water vapor, is calculated as 15.18 mm of Hg. Now, from the saturation properties of water, we know that the PS, that is the saturation pressure, is always corresponding to the dry bulb temperature. So again, we move on to that steam table and look for the value of saturation pressure corresponding to 35 degrees Celsius of dry bulb temperature. So the saturation pressure is coming out to be 42.4 mm of Hg. So having calculated the value of partial pressure of water vapor and the partial pressure of the water vapor when the given sample of the moist air is saturated at the same temperature. So PV upon PVS or PS is nothing but the relative humidity. So we just determine the ratio of these two, PV and PS. So relative humidity comes out to be 36. Now we can determine the humidity ratio or the specific humidity. It's very simple using the expression small w or omega is equal to 0.622 PV upon P minus PV. PV is the partial pressure of water vapor and P is the total pressure. So PV we have just calculated as 15.18 divided by the total pressure is 750. So the specific humidity or the humidity ratio comes out to be 0.01285 kg of water vapor per kg of dry air. Now, dew point temperature is always corresponding to what? It is always corresponding to the partial pressure of the water vapor. So, saturation pressure is there. It is 15.18 mm of Hg. So, we just look at the value of the saturation temperature given in the steam table corresponding to saturation pressure of 15.18 mm of Hg. So this temperature comes out to be 17.7 degree Celsius. So this is nothing but the dew point temperature. Now the partial densities of the dry air part and the moisture content of the water vapor part can be calculated using the expression density of the dry air part is Pa upon Ra into T. Now the partial pressure of the dry air part is nothing but the total pressure 750 mm of Hg minus partial pressure of the water vapor content multiplied by, so this is basically a figure which converts this value into the Pascal directly. So Ra is 287.1 and temperature here has to be in Kelvin. So 273 plus dry bulb temperature is 35 degrees Celsius. So partial density of the dry air part comes out to be 1.1086 kg per meter cube. Similarly, we shall calculate the density of the water vapor content also. So it's going to be partial pressure of the water vapor divided by Rv into T. So putting in all the values in this expression will give us a density of water vapor content as 0.0143 kg per meter cube. Now density of the moist air is going to be the summation of these two densities, partial densities, that is the density of the dry air part and the density of the water vapor content. So adding up these two values 1.1086 and 0.0143, it gives us a figure of 1.1229 kg per meter cube. So this is going to be the density of the moist air. Now the enthalpy, specific enthalpy of the moist air is very easy to calculate using this expression. H is going to be Cpa into T, this is the enthalpy of the dry air part, plus omega times 2500 plus 1.88 into T, where T is the dry bulb temperature, omega is the specific humidity. So everything is known to us, T is known to us, omega we have already calculated here. So just we insert all the values in the expression and we come across the value of the specific enthalpy of the moist air as 68.15 kilojoules per kg. The statement of the fourth numerical problem on the psychrometry goes like this. A room 7 meter by 4 meter by 4 meter is occupied by an air water vapor mixture at 38 degrees Celsius. The atmospheric pressure is 1 bar and the relative humidity is 70%, and we have to determine the humidity ratio, dew point, the mass of dry air and mass of water vapor. If the mixture of air water vapor is further cooled at constant pressure until the temperature is 10 degrees Celsius, we have to determine the amount of water vapor. So let us quickly look at the values which have been offered to us. We have been given a room having a volume of 7 meter by 4 meter by 4 meter, making it a total of 112 cubic meter. So this is nothing but the volume of the room, and of course the moist air would be present in this room. So the volume of that moist air is also going to be the same thing, and volume of the dry air part and volume of the water vapor content will also be 112 cubic meter. Dry bulb temperature of the moist air is given as 38 degrees Celsius, which is 311 Kelvin, and total barometric pressure is 1 bar, and the relative humidity has been given as 70% or 0.7. So we just go with calculating the humidity ratio. First of all, let us find the partial pressure of the water vapor. From the steam table, we find that the saturation pressure of the vapor corresponding to a dry bulb temperature of 38 degrees Celsius is what? It is PS. So we just move in that steam table and look for the value saturation temperature of 38 degrees Celsius, and the corresponding value of the saturation pressure in the next column would be PS, and it is going to be 0.06624 bar. Now we know that the relative humidity phi is nothing but PB upon PS. So phi has been given to us as 0.7. So with the help of this expression, we can determine the partial pressure of the water vapor. So it comes out to be 0.7 times PS. So it is going to be 0.046368 bar. We know that the humidity ratio is given by the expression W is 0.622 PV divided by P minus PB. So all the values are known to us. PV we have just calculated here, and the total barometric pressure is given to us as 1 bar. So everything is known to us. We just put in the values in this expression. So specific humidity or the humidity ratio of the moist air comes out to be 0.0302 kg per kg of dry air, or we can express it in grams per kg of the dry air as 30.2 grams of water vapor per kg of. Now, since the dew point temperature is the saturation temperature corresponding to the partial pressure of water vapor, so therefore using the steam table we find out the corresponding value of the temperature which is corresponding to a saturation pressure of 0.046368 bar, which is nothing but the partial pressure of the water vapor that we just calculated in the previous slide. So corresponding to this saturation pressure, the saturation temperature value is 31.56, and it is nothing but the dew point temperature. Let Ma is the mass of the dry air and Pa is the partial pressure of the dry air. So it's going to be the total pressure minus the partial pressure of the water vapor. So total pressure is given to us as 1 bar. Partial pressure of the water vapor we have just calculated it as 0.046368 bar. So that expression gives us a value of the partial pressure of the dry air as 95363.2 Pascal or Newton per meter square. Now we know that Pa into V is Ma into Ra into Td, which is nothing but simple ideal gas equation, Pv equal to mRT. So with the help of that, we can determine the mass of the dry air part. It is going to be Pa into V. Of course, the moist air would be present in the whole volume of the given room. So total volume of the given room is 112. So V is 112 cubic meter. Ra is the gas constant for the dry air part, it is 287, and temperature has to be in Kelvin here, so it is going to be 311. So that gives us a figure of 119.7 kg of dry air. Then mass of the water vapor can be calculated using the expression of specific humidity. Specific humidity given by W or omega is nothing but mv upon ma. We have just calculated ma here. We know the value of omega already calculated earlier, so this value gives us a mass of that is water vapor content as 0.0302 into 119.7 as 3.61. Now this is bit important part of this numerical problem. We have to determine the amount of water vapor condensed if the sample of air is reduced to a temperature of 10 degrees Celsius. So earlier we were at point number A. So it was corresponding to 38 degrees Celsius of dry bulb temperature. So when the given sample of the moist air holds the moisture in this thermodynamic state, it is definitely unsaturated air. So the partial pressure corresponding to this point A is always the partial pressure of the water vapor. If this given sample of the moist air is cooled at constant pressure, eventually it reaches the dew point temperature, which we calculated as 31.56 degrees Celsius. And if the cooling is carried out beyond this point, the condensation of the moisture will take place. So here definitely when the given sample of air is cooled down to a temperature of 10 degrees Celsius, which is much below its dew point temperature, so definitely it will lead to the condensation of the moisture. That is, the moisture content of the air is going to be reduced, because a certain amount of water vapor will be drained out of it once the air becomes saturated. So if the temperature is 10 degrees Celsius, the air will be saturated before some water condenses out. So definitely the thermodynamic state of the air will be still saturated, but it will be far below this point number G, because at point number G the temperature is 31.56 degrees Celsius, and the sample has been cooled somewhere between this 31.56 and 0 degrees Celsius down up to 10 degrees Celsius. So over here will be the thermodynamic state. So moisture content is going to be reduced, because when we look at the saturation pressure corresponding to 10 degrees Celsius, it is much lesser than that. So since the partial pressure has gone down, it definitely reflects that the moisture content of the air has been reduced. So it is only possible when the air is cooled to a temperature below its dew point temperature. So when it is cooled below its dew point temperature, then the removal of the moisture will take place. That will also bring down the partial, that is the saturation pressure of this water vapor content. So we know that the 10 degrees Celsius, the corresponding value of the saturation pressure is 0.01227. This is the partial pressure of water vapor as well as the saturation pressure, because the air is already saturated at this particular 10 degrees Celsius temperature. So now we determine the humidity ratio or the specific humidity using this value 0.622 PV divided by PV minus PV. So it is going to be 0.01227. Mind it, the 0.021227 is nothing but the saturation pressure corresponding to a saturation temperature of 10 degrees Celsius. So we determine the specific humidity now as 7.73 grams per kg of dry air. So when the moisture was present in that unsaturated air at point number A, means when the given sample of the moist air was at 38 degrees Celsius and there was a certain value of the partial pressure of the water vapor content, we had certain value of omega. So we know that the pressure of the dry air is going to be the total barometric pressure minus the partial pressure of the water vapor content. So it's going to be 0.98773 bar. So with the help of that, we again determine the mass of the dry air part as Pa into V divided by Ra into T. Volume of the room is not going to be changed. So Ma is now 136.2 kg. So mass of the water vapor, we will calculate it using this new value of the specific humidity. So this is going to be 0.00773 into 136.2 kg of dry air. So that gives us a new value of the mass of the water vapor, which is now available at 10 degrees Celsius in saturation state. So amount of the water vapor condensed would be that is the earlier mass of the water vapor which was present in that unsaturated moist air sample minus the mass of the water vapor which is now present when the given sample of air has been cooled down to a temperature of 10 degrees Celsius. So this mass of the water vapor is now 1.053. So taking a difference of these two masses of the water vapor will be the amount of water vapor which has been condensed out. So it comes out to be 2.557 kg